Avogadro's law relates volume and moles. We've heard Avogadro's name before, right? There's a number named after him. And it was his work with gases that led to the concept of the mole and eventually to that number that bears his name, 6.022 times 10 to the 23rd. So what happens if the amount of gas changes? So what he did was he measured the volume of a gas at a constant temperature and pressure while he changed the amount of gas. He didn't know what a mole was yet, but put more gas in, right? This should make sense. You start with, say, a certain amount of gas, and you add more gas, and the volume goes up, right? Think of blowing up a balloon, one breath, and then you blow in there again. Is it going to get bigger or smaller? Well, it does. It's going to get bigger because you put more air in, right? It's a linear relationship. The volume of a gas increases linearly with the number of moles in the sample. And this was first formally stated by Avogadro. He was born the same year our country was born, so he probably did this around 1800. So we can express Avogadro's law as the volume is proportional to the amount of moles. The volume of a gas is proportional to the number of particles of the gas. It's not proportional to the mass necessarily. The relationship with the mass is a little bit different, but it's proportional to the number of particles. So that can be expressed this way: V1 over N1 equals V2 over N2. Doesn't have quite the same ring to it as V1 over T1. V1 over N1 equals V2 over N2. You blow into a balloon, you're adding more gas molecules, you increase the volume of the gas. Okay, a 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? So let's make a table. 1 and 2. So we have 4.8 liters. That's the volume, right? And 0.22 moles, that's the amount of gas, that's N. And we want the volume to be 6.4 liters. So here's our table. We can find out what N2 is. V1 over N1 equals V2 over N2. So cross multiply, rearrange the equation. We should come up with N2 is equal to V2 times N1 divided by V1. So then we put the numbers in. Volume 2, 6.4 liters. Amount initially, 0.22 moles. Divided by the initial volume of 4.8 liters. So liters cancel out. 6.4 times 0.22 divided by 4.8. So N2 equals 0.2933 moles. Does that answer the question? This question's a little tricky. This is the sort of a tricky question that you should expect on an exam, okay? Because I'm going to teach you how to do it, right? So they're asking, how many additional moles of helium gas must be added? what did we calculate? The total moles when it is 6.4 liters. So we've got the sample, maybe it's a balloon, and it's at the correct volume now. What we calculated was the moles of gas that are in that sample at the correct volume. The question asks, how many moles do you have to add? So we know how much we started with. We know how much we end up with. To figure out how much we added, we subtract. This seems, to find out how much you added, you need to subtract. That just sounds contradictory. So we're going to end up with 0.2993 moles. We started with 0.22 moles. And so that difference is 0.0733 moles. That's how much has to be added. This is a subtracting problem, so in terms of significant figures, 2 decimal places, 2 decimal places, 2 decimal places in the answer. So the answer to the question is 0.07 moles. If this was a mastering chemistry problem and you stuck this in, it would say, nope, try again. Any questions? Let's do another one. Chemical reaction occurring in a cylinder equipped with a movable piston produces 0.58 moles of a gaseous product. If the cylinder contained 0.11 moles of gas before the reaction and had an initial volume of 2.1 liters, what was its volume after the reaction? Every semester during lecture I say, I need to change this problem, and then I forget, and I don't. I don't like this problem. It's not clear to me what it's really getting at. So you had this much, you had blah, 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 blah. You had 0.11 moles of gas before, and the reaction produces 0.58 moles. Well, did this amount get used up, or is this adding on to that? It's not real clear to me. We're going to assume that this was the original gas was the reactant, and it got used up, and this amount was made, and so this is our final volume, and this is our initial volume of gas. The wording on this is not great. So just going through and bringing the numbers into our table in the order in which we encounter them. 0.58 moles, so that's in a column called N. So we're seeing that this happens. It contained this and had this volume before. So these two go together. 0.11 moles and 2.1 liters. So I'm going to have to put this 0.11 down here and the 2.1 liters. One and two are not necessarily initial and final. They're just different conditions. So I'm looking for V1. V1 over N2 equals, no. V1 over N1 equals V2 over N2. I'm looking for V1. V1 equals V2 N1 over N2. So I need volume 2, 2.1 liters, times N1, 0.58 moles. Yeah.
Is the volume backwards? the initial is 2.1, and we thought we were looking for 2.
Right. So the question is this backwards? Because we're finding the volume after the reaction, and I'm finding volume 1, and oftentimes 1 ends up being the initial condition. In this situation, because of how I labeled them, the final is volume is 1 and the initial is 2. I did that kind of intentionally because I'm trying to teach those who are challenged by problems like this that you can just go through the problem and pull these numbers out in order. Which one you call 1 or 2 doesn't matter for gas laws. For things like calculating a delta T when you're doing calorimetry, it matters. Final and initial are important because it affects the sign. Here, the important thing is that we call them, that we get this 0.58 associated with the correct volume, and that we keep the 0.1 and the 2.7 together. One thing you could do if that bothers you, you make your table and you're like, oh, this is going to be confusing to me. Switch the numbers. Just erase those and say, oh, well, I'm going to call this 2 and I'm going to call that 1. So you could do that. It's an excellent question. Then I'm going to divide by into 0.11. So V1 is going to be 2.1 times 0.58 divided by 0.11. $11.07. And the unit would be liters, and it would have 2 significant figures. So 11 liters. Think about it and ask yourself, does it make sense? So we started out with 0.1 moles, 0.11 moles, and this volume. And then afterwards, we've got this amount of gas. That's more gas, right? So then we expect that the volume would increase, and this is larger than the 2.1. Any questions? Yeah.
I get on this, but wouldn't it just be easier to do the ratio?
If ratios make sense to you, yes, it would. If ratios do not make sense to you, it would not. So, since at least one person's interested, let's look at how that might look. And then if you don't, for those of you who don't like it, you can just plug your ears and say la 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 quietly to yourself. So the ratio method for doing this is look at what you're starting with. So we're trying to find the volume after the reaction. So we're going to start with the initial volume. The initial volume was 2.1 liters. And so I can do a ratio and find my final volume. The ratio here is going to be the thing that's changing. Here it is the amount of moles. And which number you put on the top or the bottom depends on whether the volume is supposed to get larger or smaller. So we started with 0.1 moles, and we're making 0.58 moles. This is a larger amount, and so we know the volume should get larger. So then I put the larger number on top, 0.58, and I put the smaller number on the bottom, and we end up with the same number. Is that what you mean? Yeah. If that makes sense to you, it is a lot faster. The problem is, for most students, you're like, what? How'd you do that? It's like voodoo or something, right? It's like magic. Yeah. So if that doesn't make sense to you, do the equation. So in the tortoise and the hare, right? The tortoise was just slowly plodding along, and the hare was, running all over the place. Could the hare have won the race? Absolutely could have won, but he wasn't very serious, and he got distracted, right? the tortoise, in that story, the tortoise always wins, right? So if this doesn't make sense to you, just be the tortoise and win the race, okay?